base register. The base register tells the CPU that when we are going to run an application, and let's say, for instance, the instruction, the first instruction that we're going to run is at address 0. But physically, that instruction itself is not at address 0 in memory. So what happens is it uses the base register where your process gets loaded in. So let's assume we take this one as an example, the one that's highlighted there. This process itself, it has a base address of, what is it? I'm just going to say 300,040. Right? That is the base address. And then the first instruction that we're going to execute is at address 0. So it takes 3,000, 300,000, whatever it is, plus the actual address of the application of the instruction. And then it knows where to go find that actual instruction. The limit register is used to ensure that when we do a request for a specific memory address, that memory address is within the limit of the assigned block of memory for the specific process. So in this case, the limit process of the limit register 1209000 is the highest number of the actual memory address that we find in the process itself. So remember I said the process potentially starts with memory address 0, and then the highest address is 1209000. And the limit address really just makes sure that we never override or go potentially into the memory belonging to another process. Here's a nice diagram that describes this principle. So in this case, the CPU has a specific address that it wants to access. It looks at the base address, is the base address there, greater than the base address, yes it is. Then it adds the base plus the limit and checks that, and then you can access it. And it uses the base register to figure out where in the memory it has to. If it's not within these ranges, meaning if it's the base register is incorrect or the limit register is incorrect, and you try to access something, then a trap will occur. Traps in the operating system, which basically means there's an address error. So you're trying to access something not belonging to your process. So that's the first thing that you need to understand. You got the base register, limit register that helps you position exactly where in the memory we have our process. Okay, programs of disk ready to be brought into the memory to execute format input queue. That basically means that if we run a program, we basically have this input queue of places to put our process or the information. And they basically, if it's not without any support, we basically load it into 000. However, that's inconvenient because we want to potentially load it into another area in our memory. So we don't want to just immediately go and load in the memory address 000. We want to load potentially somewhere else. And that is basically again where we find the base register that helps us position it in the correct place. So we load it into the correct place. Finding the instructions and data from memory. Okay, this is basically explained to us if we compile a program. That program, when it's compiled, says I want to access, let's say, a function at memory address 500. But who said that memory address 500 is exactly where we're going to be inside the actual memory of the computer? Because it can be anywhere. Remember these base and limit addresses ensure that we can potentially shift it around. There are different approaches to handle this relocation principle. This is what they call compile time. That is where at compile time you set absolute addresses of where it can always be loaded in. That is a very poor choice, and it was typically used with the old computers. You can also handle that through what they call load time. So that basically means as soon as the process loads in, then it basically looks for the code as it gets loaded into the memory of the computer. Any references to, let's say, actual memory addresses can get modified. That's another approach. Or they can have it run at execution time, and that is where we need hardware support, such as base and limited registers. That is what it's important. Okay, let's talk about multi-step processing of the user program. So just quickly how this works. When, and this kind of should explain to you how do we know where things are loaded in memory. When we've got our source program, whether it's a C++ program or whatever, the first thing that you do is you send it to a compiler. Now obviously when you're writing assembly code, you don't send it to a compiler. It's already in assembly language. Once you send it to the compiler, it becomes what they call an object module. The next step is effectively the linker, and at this point, other object modules get linked into the system, and I don't have it open anymore, but at that stage, you can take loadable modules, and you can make it part of the actual program itself, each with its own section of code. And then you basically load this module into your, well, basically the module here, and then you create what they call a loader, which is part of the actual exe file. So every time you run double-click the actual exe file, the loader program starts running. The loader program knows exactly what libraries have to be included and where in the memory you want to put the specific program, and then here in memory 1 and memory 3, so basically just when you run the system, it basically starts grabbing the necessary information that we have. And you'll see that this last step, this dynamically loaded system libraries, it's important in multi-processing systems, because if you run more than one process, both of these processes use the same library. Do you have to load it twice in memory, or can you just load it once in memory? And both processes refer to it once, often the same copy of it. And that is why, well, these are some of the strategies that we use inside our memory. This brings us to the principle of logical and physical address spaces. And this is the time.